The next chapter that we are going to look at is on the basic electrical quantities. So last chapter we dedicated it for network and understood what a network is. The second part of the subject is the analysis. So what are we going to analyze essentially? So we are going to analyze some of the basic electrical quantities in an electrical network. So that's why this chapter is very important and basic for understanding what a network is and how the basic electrical quantities behave in a network. In the last section, we discussed on network and circuit. We also discussed on node, branch, the types of nodes that we use for analysis. We discussed on loop and mesh. We also discussed on planar network and non-planar network. So in this section, let's split part and understand some of the basic quantities that we use for analysis. First, we'll start with charge and its associated quantity, electric current. Then we'll discuss on electric potential and its associated quantity, electric potential difference, followed by energy and power. Once we go through these basic electrical quantities, we'll discuss on the sign convention that we'll use for any questions in our network analysis. So before moving into the individual details, we can note that all these quantities which are mentioned here, these are measurable quantities. For example, if we measure current, we note in terms of amperes. This is just like measuring distance with meter, time with seconds. We'll look into the details in the upcoming slides, but the point is, whatever the quantity that we are analyzing, our measurement has to be legible and should be understood and used by anyone who is reading the measurement. Essentially, we need a specific system of units for any quantity that we are measuring. So such an internationally accepted measurement language is known as International System of Units. We all know in terms of SI units. So there are basically 6 principal units defined in the SI system. So with these principal units, the unit of all other physical quantities can be derived. One great advantage of using this particular system is that it uses prefixes based on the power of 10. And this can be used to represent some of the larger units as well as some of the smaller units. Example, we use centimeter, millimeter, kilometer. This all represents your meter, and the centi, milli and kilo that we are speaking are the prefixes to the base quantity, which is the meter. So as we are dealing with electron level information in network analysis, we will mostly use these prefixes, which are milli corresponding to 10 power minus 3, micro corresponding to 10 power minus 6, nano for minus 9, pico for minus 12, and femto for minus 15. With this note, let's move to the individual electrical quantities. The first and the most basic electrical quantity is the charge. So charge is the electrical property of the atomic particle that make up the matter. So we experience charge in our day-to-day life. We all would have charged the comb by friction and make it attracting to the pieces of paper. If not, please do this static charge experiment and have some fun. So coming to the context, SI unit for charge is coulomb, and we represent it with capital C. We know that all the matter is made up of some of the fundamental building blocks. These are called atoms. Each atom consists of the basic components such as the electrons, protons, as well as neutrons. Such an atom with equal number of protons and electrons are termed as electrically neutral. If this atom loses an electron, basically if this electron gets out of the atom, then this particular atom becomes a positively charged ion. This is because the positive charge starts dominating comparatively to the negative charge. Similarly, when an atom gains an electron, this negative charge starts dominating because of more electrons. This is now termed as negative ion, and the electrical property of such an ion is the negative charge. So, from this, it is clear that an electron carries a negative charge, a proton carries a positive charge, but how much? How much charge does it carry? From some experimentation, it is found that an electron or a proton carries 1.6 times 10 power minus 19 coulombs of charge. This is the magnitude for charge in an electron, charge in a proton. The magnitude is same, but they are opposite in nature. So that is why equal number of protons and electrons in an atom makes the atom electrically neutral. One electron contributes to 1.609 into 10 power minus 19 coulomb. Then essentially 10 electrons contribute to 1.609 into 10 power minus 19 times 10, right? So similarly, n electrons contribute to n times 1.609 into 10 power minus 19 coulomb. So basically, our charge q on a given ion can be represented as n into E, which is the number of electrons into the charge on an electron. So this is also applicable for proton. It is just the same. It is the number of protons times the charge on the proton. Now coming to the quantity coulomb that we are discussing, this is not a very small amount of quantity. A coulomb is a large quantity. For instance, if we could see, if one electron contributes to 1.609 into 10 power minus 19 coulomb, then how much number of electrons are required to give 1 coulomb? So basically that is 1 by 1.609 into 10 power minus 19. So which is basically 6.24 into 10 power 24 electrons, which combines to form 1 coulomb. So basically we need 1 followed by 24 zeros. These many number of electrons should be there to give me 1 coulomb of charge. Please note that the charge can neither be created nor be destroyed. So charge can only be transferred from one place to other. So this means the algebraic sum of charges in a given network is always constant. So please note this. We'll use this multiple times in our network analysis, and the application is also wide. Now we have defined and hyped enough about the charge. Let's make him useful by asking the charge to flow. So basically, a unique feature of this electric charge is that it is mobile. That is, it can travel or transfer from one place to another. Yeah, it can move. Basically, it can be transferred from one place to another where it can be converted into another form of energy. For example, when a conducting wire consisting of several atoms, let's say this is a conducting wire which consists of several atoms, is connected to a battery, something like this. For now, consider the battery as a team coach who compels you to move. In this condition, the positive charge travels in one direction and the negative charge travels in its opposite direction. So this motion of electric charges creates something called electric current. So the convention followed is to take the current flow as the motion of positive charges. But actually speaking, current flowing in a conductor is due to the movement of negatively charged electrons. Anyways, let's stick to the convention. So basically, we can also take a fan as an example. Basically, when you switch off the or switch on the fan in your vicinity, charge is basically transferred from the grid to your fan, and it is being utilized as the mechanical energy where it rotates. Also, as we saw, the current whatever is being created is because of the flow of charges, which means the more is the flow of charges, the more is the electric current. So this can be mathematically represented as I is equal to the rate of change of charges. So the more is the rate of flow, basically the flow of charges, the more will be the current. So this can be now put as 1 ampere for current, which is equal to 1 coulomb per second, because C is the unit for your charge and seconds is the unit for your time. So basically, which means in 1 second, if I have 1 coulomb of charge flowing, then that is going to contribute for 1 ampere of current. It's that simple. Now inverting it back to compute the number of charges transferred for a given current, it is the same equation, which is dq is equal to I dt. Now if I am interested on the charges which are transferred from t0 to t, then it is nothing but integral t0 to t I dt. So assuming this current to be constant and t0 to be 0, then it is basically 0t and is a constant time and dt, which is basically equal to I into t. So this is what we usually see, I into t for charge. But here the assumption is that the current is constant. Please note that there are different types of current, one being the direct current, the other type is a time varying current. The most common form of time varying current is the alternating current. So direct current, as the name suggests, the current value does not change with time. So basically, it's a constant current. The charge flow will not vary with respect to time. On the other hand, time varying currents or currents where the current or the charge flow varies with time. So one popular example is the alternating current that we have in our households. All your washing machine, refrigerator, air conditioner, all this works with the alternating current. So this might look puzzling now how this is going to work, but don't worry, we'll discuss this in detail when we discuss on the alternating current. Also, as we discussed, current is nothing but the movement of charges. So if we term it as the movement of positive charges, then this is positive 5 ampere. The same current can be represented as movement of electrons in the opposite direction. So basically these two are essentially same. If I mention positive 5 ampere in one direction, then it also means I have a negative 5 ampere flowing in the other direction. So both these notations can be used interchangeably. So now let's look into some of the questions. So first is on how much charge is represented by 4600 electrons. So we know that the charge is equal to number of electrons into charge in a particular electron, which is equal to 4600 times 1.6 into 10 power minus 19 coulomb. So which is, you can compute this. So this is the amount of charge which is represented by 4600 electrons. We also should be careful that the charge in an electron is negative. So we essentially need to have a negative value of coulomb. The next question is on the total charge entering a terminal is given by Q is equal to phi t sine 4 pi t. So the charge is phi t sine 4 pi t millicoulombs, and the current at 0.5 seconds is the question. We know that current is nothing but rate of change of charges, so which is equal to d by dt into phi t sine 4 pi t. Of course, millicoulomb and time in seconds, so basically it is millicoulomb per second. Coulomb per second is nothing but your ampere, so it is milliampere. Let's preserve this till the end. Now taking this, phi is your constant and it is d by dt of t sine 4 pi t. Okay, so this is simple, which is your d by dt of uv will be equal to u dash v plus uv dash. This is 5 into, let me preserve t, and differentiating 4 pi sine 4 pi t will be sine differentiated to cos, and 4 pi comes here, and keeping sine 4 pi t constant, I am going to differentiate t, which is 1. So which is nothing but uv dash plus u dash v. I'm sorry, uv dash plus
u dash. So essentially this comes to 5 into, and I have to apply this for 0.5 seconds, which is nothing but 1 by 2. Now this becomes simple, 4 pi into cos 4 pi 1 by 2 plus sine 4 pi by 2. That's it. So this becomes cos 2 pi. Your cos 2 pi becomes 1. Sine 2 pi becomes 0. So it's only 5 into 4 pi, which is nothing but 10 pi. 10 into 3.14, which is 314 milliamperes. Next is to determine the total charge entering a terminal between t equal to 1 second and t equal to 2 seconds. So we need to essentially find charge, and we are given with time. We are given with current dt square minus t. So charge in terms of current is nothing but integral I dt, and time is also given between 1 and 2. So basically charge is equal to integral I dt. This is also simple, which is t cube by 3 minus t square by 2 applied between 1 and 2. So this becomes your 8 minus 1 minus 4 minus 1 by 2. 7 minus, this is 3 by 2, which is 1.5. So this would be 5.5. And here it is full.
The next quantity on our list is electric potential and potential difference. To understand what potential is, let's take the example of two North Pole magnets placed apart from each other. We know that the North Pole and North Pole repel from each other. So if I need to move one magnet towards the other, I need to spend some energy or do some work. We also know that the more I move it closer to each other, the more it will repel from each other. Which means the more I move it closer, I need to do more work or spend more energy to do that process. Why is this happening? This is happening because each magnet produces its own magnetic field. So this magnetic field will be stronger at a place closer to the magnet, and as we move away from the magnetic field becomes weaker and weaker. So if I take a distance infinity, which is very far away from the source magnet, then I'm not going to experience any effect because of the source magnet. So technically, I can term it as the potential at this point is very much higher compared to the potential at this point. So the potential decreases as I move away from the source magnet. And also the potential at a point which is at the infinity or at a very larger distance is almost equal to 0. So this is well understood. So now if I take a test magnet and if I try to move it closer to the source magnet, then essentially I need to do more and more work. So technically I can term it as work has to be done by an external agent in order to move this particular test magnet from a lower potential region to a higher potential region. So I hope the concept of potential at a given point is clear. Let's apply the same to the electric potential. We have understood potential from the magnetic perspective. Let's apply the same for the electric charge. So the source charge here is similar to the source magnet, and the test charge here is similar to the test magnet. So any charge will produce electric field. So just like how we saw, a magnet will produce its own magnetic field, electric charge will also produce an electric field. And this electric field will be diminishing as we move away from the charge. So basically, with this definition, electric potential at a point A due to the source charge, we can define it as the amount of work that I need to do to move this unit charge from infinity to this point. So we understood that the potential at a point away from the source magnet will be lesser than the potential at a point which is closer to the source magnet. Same applies for the source charge also. So if I take multiple points in this, let's say point B, point C, point D. So the potential at point B is greater than the potential at point C, and is greater than the potential at point D, and is greater than the potential at point A. This is because the amount of work that I need to do to move this test charge from infinity to A is less compared to the amount of work that I need to move it from infinity to D. Similarly, it will be more when I need to move it from infinity to C, and it will be much more when I need to move it from infinity to B. So as we move closer to the source charge, the more is the work that I need to perform. Now that we have covered on the basic quantities, which are charge, current, potential and potential difference, let's look into the next two quantities, which are energy and power. So though current and voltage, which is the potential difference, are sufficient for us to understand how an electric circuit works, we practically speak in terms of power and energy. So basically, we know that when we have a 60-watt bulb and a 100-watt bulb, the 60-watt bulb obviously glows less brighter compared to the 100-watt bulb. So we have it in our terms of usage. Also, we pay our bills and the electricity bills basically in terms of energy that we have already consumed for the past month or two. So basically, practically, we speak in terms of energy and power to rate a certain element such as a bulb, and also to compute what is the amount of energy which is used upon by a particular customer or consumer in a household or an industry or something. So we need to understand what energy is and power is. So we have enough discussed on energy. Energy is nothing but the amount of work that is done. So work done by the external agent in moving a charge from one point to other is something what we call the work, and it's on any charge that is being consumed. Basically, we define the potential as the amount of work done per unit charge, whereas your energy is the actual work which is being done. So the symbol for energy would be either U, or sometimes we'll also use W, but U is the standard symbol that we could use for. So if we could compute, your U is nothing but, we already seen it is minus Q times integral A to B E vector or DL vector. If the amount of energy that I or the work that I need to move the charge Q from A to B is given by minus Q into integral A to B E vector or DL vector. So we have already termed this minus integral E vector or DL vector as potential difference between A and B, which is VAB. So my energy or the work is can be represented as Q into V. So as simple as that. Basically, when I want to move a charge of charge Q from a point B to A, which is having a potential difference of VAB, then the amount of work that I need to do is just the multiplication of your charge and the potential difference between them. So basically, if the potential difference between 2 points is very less, then easily you can move the charge. At the same time, if the charge is a lighter charge, then also the amount of work done or the energy spent to move this charge is lesser. So your work is equal to Q into VAB. Now coming to the next term, which is the power, which we normally use to. The symbol for power is P, and the unit for it is watt or W, just by simple. For example, the 60 watt, 100 watt, that's how we mention it. So power is nothing but the rate at which the energy flows. Just like the rate at which the charge flows is termed as current, the rate at which the energy flows is termed as power. So how significant it is? For example, we have two bulbs, with one with 60 watt and another with 100 watt. and we connect it to a constant voltage source. Let's say you take a battery and connect it to a bulb. So which bulb do you think glows faster? Obviously the 100-watt bulb. It glows brighter compared to the first one. So it glows very less. So why is this done? This is done because the energy that I'm supplying is same, but the power that it utilizes is different. Basically, my 60-watt bulb utilizes the same amount of energy in a prolonged time, whereas my 100-watt bulb, it basically consumes the energy much faster. So we could experience a slower draining of battery in 60-watt bulb and a higher draining of battery in your 100-watt bulb. So more is the wattage that you use, the more is the more fast is my energy is going to drain. So basically, this is why we get higher bills for our air conditioners compared to our fans. So your fans have lesser power, watt and requirement, as well as your air conditioner requires higher wattage requirement. So basically, power is what we use in the real world terms. So we also need to understand from circuit perspective how it is impacting the power in a circuit. So as we defined, power is the rate at which the energy flows, which means how fast my energy is flowing in a given element or a circuit. So power is nothing but rate of flow of my energy. So we have already termed energy as Q into VAB. So which is my Q into V in general. So my power is equal to d by dt of Q VAB. So which is nothing but d by dt of Q into VAB, which is nothing but dq by dt is simply the rate of flow of my charges, which is nothing but my current. So power PT is given by I of t into V of t. So this term that we have derived is the instantaneous power. What is instantaneous power? What is the power at that particular instance t? For example, we can have a different power consumption in 1 second and different power consumption in 2 seconds. So the PT is nothing but the instantaneous power, and it is given by the multiplication of instantaneous current IT and the instantaneous voltage VT. We'll see the application of this in some questions down the line. But for now, energy is the term which is the amount of work which is being done. Power is the term which represents how fast my energy is being consumed in a given circuit. So now that we have covered charge, current, potential, and potential difference, which is nothing but the voltage, energy, and power. Okay, so given the understanding of the different quantities, let's summarize it. So we discussed charge. Charge is given by the symbol Q, and this is the most basic electrical quantity of a given circuit or a given electric circuit. So charge, the units of charge is coulomb, which is represented by C, and current is the rate of flow of charges, which is given by dq by dt, and the unit for it is ampere. Electric potential, we discussed it. It is the work done in moving a unit charge from infinity to that point. So its symbol is V, and the unit for it is capital V, which is the volt. The equation for it came to be minus integral infinity to that point, E vector or dl vector. Then we discussed on electric potential difference or voltage, which is the amount of work done in moving a unit positive charge from one point to other point. So the symbol for it is V, or in general specifically mentioning VAB, where it is the potential of B with respect to A, and the unit for it is volt. Since the difference between two voltages, the units remain the same, and the equation is minus integral A to B E vector or dl vector. Then we discussed on energy and power. Energy, the symbol for the energy is U. It is also the work done. Its unit is joule, and the equation is given by Q into V. Then comes the power. We discussed on power. Power is the rate of flow of energy. So your power is given by I of t into V of t, which is your voltage into current essentially. and the unit is given by watt. So now that we have summarized the basic quantities, let's also look on the sign convention that we want to follow for this particular lecture series for any questions that you're going to solve, and let's see how it is relevant also. For example, if you have a circuit where you have a source or any element where the current is given as leaving the positive terminal, then we assume that the power is being delivered by this element. So basically, if we have a positive terminal and the current leaves the positive terminal, we assume that this element is delivering the power. On the other hand, if we have a positive terminal and your current enters the positive terminal, we assume that the power is being absorbed by that element. Same is the case by the load. As for example, in the load, if you assume a positive negative like this, and if you see the current is entering the positive terminal, then this element is absorbing the power. And on the other hand, if now the current leaves the positive terminal, it is assumed to be delivered. So this is the initial assumption that we'll have in any of the problems or the questions. Then based upon the current direction with respect to the voltage polarity, we deduce whether the power is absorbed or delivered. This is what we mentioned here. Once we do the question with this assumption, then we, to verify whether our assumption is correct or not, we calculate the power, which is the voltage and current multiplication. If the power comes to be positive, then our assumption is correct. If it comes to be negative, then our assumption is wrong, which means we will see examples, which means like if we would have assumed observed and proceeded with the problem and the power came to be negative, which means the power is actually delivered. So we can conclude that the power is delivered. So a few examples are given here. For example, here the current seems to be entering the positive terminal. So the assumption is the power is being absorbed. With this assumption, I'll proceed and calculate the power, which is voltage into current. If the resultant of this comes to be positive, then our assumption is correct. My power is being absorbed. If it comes to be negative, then we need to update it as the power is being delivered. So same a similar case where here I have my current leaving my positive terminal. Hence the assumption is the power is being delivered. With this assumption, I should proceed for power computation, which is voltage into current. If it comes to be positive, then my assumption is correct, it is being delivered. If it comes to be negative, then my assumption is wrong, which I mean I need to update it to absorbed. So let's see how this assumption that we are doing is valid. If you take a battery and a circuit something like this, we know that the electric field travels from positive to negative. So this also we saw from the source. Basically, we had a source and our electric field is outwards to it. So basically, my electric field flows from higher potential to lower potential, which is plus to minus. So if we take that into account and use it here, basically if we could see, this is the battery and this is my load. So external to the battery, I could see my charge flows in the direction of electric field. So a charge, since I assume the current flow as the moment of positive charge, so here if we could see, the charge flows in the direction of electric field. The electric field is also from plus to minus and my charge is also moving in the direction of plus to minus. But internal to the battery, if you could see, internal to the battery, I have my electric field, which is always from positive to negative. So I have my electric field in this direction. But for the flow of charges, it has to be a complete flow of charges, which means my charge is flowing from negative to positive. So this is my flow of charge and this is my flow of electric field. This is my electric field. So basically, external, as a summary, what we could tell is external to the circuit, my charge and electric field are flowing in the same direction, which means if I have an electric field and if I have a charge, my charge moves in this direction. So basically, the circuit is not doing any work. It is just following the convention, which is basically my charge placed on an electric field will move in its own direction. So when is work done? Work is done only when it moves in the opposite direction. So basically, if there is some external force which is making the charge to be moved from one place to another in an opposite direction, only then we assume the work is being done, right? So external to the field, my electric field is this, my charge is this. So which means there is no work done by the element, the work is only done on the element, right? So if we consider this load, the work is done on the element because there is no opposing happening. On the other hand, if we take a battery, it is having an electric field from in one direction, but the charge is moving in the opposite direction, which means essentially there is a work done by the battery. So essentially in this circuit, with this understanding, we can tell that work is sorry, we can tell that the work is done by the battery and work is being absorbed or work is being utilized by the other elements in the circuit. Okay, so that's how the convention looks at, like when the current leaves the positive terminal, the power is being delivered, and when the current enters the positive terminal, it is being absorbed. That's how the convention is valid. Hope the understanding is clear. In the next session, let's look into the classification of different circuit elements.